Hi guys, welcome to ChemXplain. Hope you had a great day by now and enjoyed the series. Today we are going to have the fourth episode of the Analytical Chemistry series. In this video, we are going to start a really important concept or topic, which is chemical stoichiometry. Before we continue, don't forget to subscribe to our channel and hit that like button to make us sure that you like this series. Now, let's go. What is chemical stoichiometry? We can say stoichiometry is the quantitative relationship among the amounts of reacting chemical species. In this video, we provide a brief review of stoichiometry and its applications to chemical calculations. Okay, fine. But before we go to the stoichiometry problems, we want to make sure about 2 or 3 concepts which are really essential. They are empirical formula, molecular formula, and structural formula. I suggest before providing a definition for each of them, let's see some examples. I'm going to write 2 or 3 molecules, starting with this one. I say C2H4O2. Another one, I say C3H6O3. Or even another one, C6H12O6. Yes, each of these molecules have their specific name. For example, the first one, you tell me, huh? I'm waiting for you to write it in the comment section. The first one is acetic acid. On the other hand, the second one is glyceraldehyde, and the third one is glucose. As you can see, they have different formulas, or to be more specific, different molecular formulas, and they have different names. But there would be really interesting if you know that all of their empirical formulas are the same, and that would be CH2O. So what do you guess about the definition of empirical formula? We can say an empirical formula gives the simplest whole number ratio of atoms in a chemical compound. However, a molecular formula specifies the number of atoms in a molecule. So let's say the definition is, I'm sorry about this one. The simplest whole ratio of atoms. However, for molecular formula, we say the exact number of atoms in a molecule. Fine. But you may ask, what is CH2O? Actually, we have another molecule with this formula, and its name is formaldehyde. So we can say that the empirical formula and the molecular formula of formaldehyde is completely similar. However, it is different when it comes to glucose, glyceraldehyde, and acetic acid. Okay, I think you are somehow familiar with this concept. Now let's get to the next one, which is structural formula. Okay, to know and understand this one easier, I'm going to go with an example again. Look at this formula. I say C2H6O. So when you look at this formula, what molecule comes to your mind? For example, I can say ethanol, which is C2H5OH. Fine. So this one is ethanol. Okay. On the other hand, we can think of another one, which is CH3OCH3. Actually, this one is dimethyl ether. So let me write it here. Look, there are different molecules, but their molecular formula is the same. Actually, the formulas that we have here, I mean this one and this one, which I'm showing with the blue color, are their structural formula. So to be more accurate, we can say the structural formula tells us how the atoms are connected together. So it shows how atoms are connected together. Fine. Now, I guess you're somehow done with this. So let's head to some examples and the stoichiometry. Fine. Now, to have a clear understanding of stoichiometric calculations, we are going to talk about it in an example. So let's say sodium iodide plus lead nitrate produces lead iodide plus sodium nitrate. Okay, so the equation is complete now. However, we need to balance them. So to balance this equation, we can simply put a 2 here. Oh, I'm sorry. We can put a 2 here. And on the other side, we need another 2 here. Okay, so what does this equation mean? We can say it indicates that 2 moles of aqueous sodium iodide combine with 1 mole of aqueous lead nitrate to produce 1 mole of solid lead iodide and 2 moles of aqueous sodium nitrate. So by knowing the equation, which is balanced, we have the ratio of the substances that we need, even they are in their reaction part or even they are in the products part. So in another word, we can say by knowing the mass of the reactants, we can calculate the moles. And by knowing the moles of reactants, we can calculate the moles of the products. And by knowing the moles of the products, we can calculate the mass of the products. And this can be used vice versa, I mean, in the other direction. So by knowing this simple rule, we are going to do some stoichiometric problems together. Now, let's take a look at this example. It says, what mass of AgNO3 is needed to convert 2.33 grams of Na2CO3 to Ag2CO3? So after this part, we are going to talk about part B of this example as well. But before doing anything, before starting any calculation, it's really important to find the whole equation. So we can say Na2CO3 plus AgNO3 can give us Ag2CO3 plus NaNO3. To balance this equation, we can add a 2 on this side and a 2 on this side. Okay. The question says, what mass of AgNO3 is needed? On the other hand, it gives us the grams of Na2CO3 and also the molar mass. So let's go, we can say 2.33 grams of Na2CO3 divided by 106 grams per mole is equal to 0.02198 moles. Okay, so this is the mole of Na2CO3. Now, look at the equation again. Na2CO3 and AgNO3. We can say each mole of Na2CO3 requires 2 moles of AgNO3 to react with. On the other hand, we have the moles of Na2CO3. So to calculate the moles of AgNO3, we can say 0.02198 times 2. It can give us the moles of AgNO3. So that would be 0.04396 moles of AgNO3. Fine. Now that we have the moles of AgNO3 and also we have its molar mass, it's really easy to convert the moles to grams. So we can say 0.04396 moles of AgNO3 times 169.9 grams per mole. So it would give us 7.47 grams of AgNO3. So this number would be the answer to part A of the question. What mass of AgNO3 is needed? On the other hand, it says what mass of Ag2CO3 is formed. Look here, we can say each mole of Na2CO3 will give us 1 mole of Ag2CO3. So the number of moles of Ag2CO3 would be still 0.02198. And also we have the molar mass of this one. So to calculate this part, we can say easily 0.02198 moles times 275.7 grams per mole. It will give us 6.06 grams of Ag2CO3. So you can see that the amount of Ag2CO3 which is produced is calculated easily. Now, taking a glance to this solution, we can see that all we did is seen here in this flowchart. Every time we go from mass to moles and from moles to mass and vice versa. So by knowing this simple rule, we can do all of the stoichiometric problems easily. Okay, I'm not going to make this video longer. Hope you enjoyed this video by now, and let us know your ideas in the comment section. And if you liked the video, don't forget to hit that thumbs up button and subscribe to our channel. Thank you so much. Hope you see you again. Until next time.